Hello, hello, hello. Hi everyone. Welcome to Vedantu JEE English. I'm Diksha Ma'am, your chemistry master teacher. So everybody do let me know if I'm clearly visible and audible to all of you so that we can start with today's session. Yes everybody, am I visible? Am I audible to all of you? And so sorry for getting late. I had some really urgent work at my home, so that's why I got late, right? Okay, so everybody, today is actually, it should be class 11th. My bad, right? This should be class 11th, definitely. That is your class 11th. I'll just change the thumbnail. I'll ask the team to change the thumbnail after that, okay? So guys, what's happening? Today is Saturday, and as I promised you that no matter, even if I have to take extra class, I will complete chemical bonding by this Sunday, and that's why tomorrow also I am taking one class, right, so that our chemical bonding can be finished, right. Now today's class is actually the hot topics of chemical bonding. First is VSEPR. You can say it's a combination of VSEPR, VBT and hybridization. How to apply all these things to answer the question, right? For example, they will give you some compound, and how do you answer that, what kind of shape or geometry it will have, right? We'll discuss about that and we'll solve some previous year questions based on that. Then we are going to cover with MOT, molecular orbital theory, again a very important theory, right? Okay, so everybody, shall I start the class? Before that, let us see. So this is the question: two types of orbitals undergoing hybridization. Which two types of orbitals, 3s and 3p, can undergo hybridization? That I told you that for hybridization they should have same or nearly same energy. That is possible here in 3s and 3p. So answer is C. Then identify the incorrect statement here. Hybridization, isolated atom from sigma bonds, number of hybrid orbitals equals to number of orbitals involved. That is also correct. Hybridization involved may involve orbitals of nth and n minus shell. That is also correct, right? This is also correct. This is also correct. So this one is the wrong statement that you have. So B is going to be the correct answer. Hello Anjali, hello Kesa, Guru, Daniel, Vanakam students, out. And happy Ganesh Chaturthi. So today, like those people who have, Ganesh tree in their homes, they are doing Visarjan of Ganesh tree, and I just witnessed that today in such a beautiful thing, isn't it? Such a beautiful thing to see everyone, devoters of Ganesh tree, right, with so much selfless kind of love they have for Ganesh tree. So it's really awesome to see all these devotees there, right? Okay, yes. So let us start the session. Wait a minute. Let me see if the board is wrongly placed. Is it? Wait a minute, guys. Let me just see that if the board is wrongly placed. I think now it's better. Okay. Yes. Okay. Yes. So students, firstly, let us talk about VSEPR. Now, here are some postulates that we should know, because from postulates they can ask you the theory points. Okay, the first postulate: which of the following is not a postulate of VSEPR theory, which of the following is not correct. For that you should know what is written in NCERT, and all these postulates are from NCERT only. I always prefer, for inorganic chemistry, you should always prefer the things that are given in your NCERT. That is everything for you, right? Now the first postulate is the shape of molecule depends upon the number of valence shell electron pairs bonded or non-bonded around the central metal atom. So he is saying that, like in the last class we discussed about steric number. That is defined by the lone pairs plus sigma bond pairs, right? So that means this steric number is going to tell us about the hybridization, and that hybridization is going to tell you about the geometry, and based on that geometry you will tell the shape. So that means everything depends upon the number of lone pairs and the number of bond pairs that you have. That means the valence pair electrons that are bonded, that means forming bond pairs, and non-bonded, that means they are the lone pairs. These are bond pairs, these are lone pairs around the central metal atom, right? Next thing is pairs of electrons in the valence shell repel. Now we know that this shape, geometry, hybridization, all these things that I ask you in the exam, that depends upon one factor, that is your steric factor, right? Steric number, that depends upon the steric number, right? So now let's understand pair of electrons in the valence shell. Now we are saying that how many pair of electrons that you have in the valence shell, bond pair, lone pairs, whatever you have, since their electron clouds are negatively charged, they will repel each other. Because what are in the pairs? You have electrons, electrons will have electron clouds, and that's why they will cause a repulsion. Repulsion between lone pair and lone pair. Repulsion between bond pair and bond pair. Repulsion between bond pair and lone pair. These are the repulsions that it will give you. These pairs of electrons tend to occupy such positions in space to minimize the repulsions. That's why you have specific shapes: linear, tetrahedral, trigonal, bipyramidal, trigonal, planar, octahedral. These are shapes because of these repulsions, because they want to minimize the repulsions. That's why they attain a specific shape, right? Next is the valence shell is taken as a sphere with electron pairs localizing on the spherical surface at maximum distance from one another. So it is taken as a sphere only, valence shell is taken as a sphere so that it can have the maximum distance and minimum. It is how it is visualized. It is visualized as a sphere, right? So that it can have maximum distance and minimum repulsions. Multiple bonds like single bond, double bond, they also show repulsions, right? Single electron pair and 2 or 3 electron pair of a multiple bonds are treated as single super pair. Now that means if I talk about a single bond, it is taken as single bond pair, right? Single bond pair. If I talk about double bond, it is also taken as single bond pair. If I talk about triple bond, that is also taken as single bond pair. That means we ignore pi bonds. Pi bonds are not considered in the steric number. That's why when I told you about the steric number here, the definition I specifically mentioned here that it is sigma bonds. Pi bonds we don't include in this. Pi bonds are not included here, right? Next is where 2 or more resonance structures can represent a molecule, the VSEPR model is applicable to such structures, right? Even like in O3, ozone, O3, in CO3 2 negative, you have resonating structures of that. Even in that, VSEPR theory is applicable, right? Now let's understand the main crux of this particular theory is that there will be lone pair, bond pair, and bond pair repulsions, right? And to maximize the distance, minimize the repulsions, they will form certain set of structures that we call as geometry, right? So if you talk about the repulsions are maximum in lone pair, then lone pair, bond pair, and minimum in bond pair, right? So that's why you will have cases of lone pair and bond pair specifically you will have, and shape is going to change depending upon that, right? Now types of repulsions in multiple bond, double bond and single bond, if you talk about, if you have 2 multiple bonds, they will have maximum repulsion, like you have double bond and double bond, okay, like you have this kind of set, Now because you have 3 multiple bonds, they are going to show maximum repulsion. If you have a set where you have a double bond, for example, you have some X here, it is linked to a double bond, and here it is linked to a single bond. Here it will be less repulsions. If you have something here where both are single bonds, in that case it will be minimum repulsions. So multiple bond maximum, then multiple bond, single bond less than that. Single bond and single bond is going to show you the minimum repulsions here, right? Okay, yes. So lone pair repulsions decreases the bond angle. This, in fact, we are going to discuss bond angle and dipole moment in the next class, and this in detail will discuss about how bond angle is going to get affected by certain things, right? So we are just learning a bit of that over here. That is lone pair repulsions, if you have somewhere, they will decrease the bond angle. Lone pair bond pair repulsions will decrease the bond angle, but bond pair repulsions are going to increase the bond angle. Okay, we'll talk about that, don't worry, just give me some time, we'll definitely talk about that, right? Okay, now let's see. One by one we are going to discuss about these cases. So wait a minute. What I'll do, I'll come to that in the next, in the last example, we'll go that what exactly is BRF5, right? We'll do that. Firstly, let's discuss different cases, okay? So, first case is, in the end, I'll make one chart for you guys so that you don't have to remember so many things, okay? Right now, just focus on understanding how we are going to proceed, right? So, for example, I'll take these examples here that we have written here, right? So, let's take the example of BeCl2. You have no idea what is this. Now, how you are going to solve this, right? Let's understand that. To solve this, what you will do? Firstly, we know that what is the steric number. Have I taught you how to calculate steric number? Yes. How to calculate steric number? To calculate steric number, so simple thing is what you will do, in fact, beryllium belongs to which group? Hydrogen, helium, lithium, beryllium, right? So it is going to be 2s2 here, 1s2, 2s2, right? So it is having 2 electrons here. But we, in fact, you know what we are going to do? Just see how many bonds it can form, right? Now if you talk about in the periodic table, beryllium belongs to which part? This is hydrogen, helium, lithium, beryllium. Is it belonging to group 2? Just remember this, okay? It's a shortcut method, okay? Just remember the group here, okay? You can calculate the steric number, you can do with that method as well. You can calculate the steric number and then you need to answer what is the hybridization. Answer will be same. Here I am just giving you a simple direct method to calculate this, right? So here it is group number 2, right? Group number 2, group number 1 makes 1 bond, group number 2 makes 2 bond, group number 13 makes 3 bond, group number 14 makes 4 bonds, right? Yes, okay. 15 makes, wait a minute, yeah, 3 bonds. In fact, it has 5 valence electrons. Valence electrons is what I am asking you, right? So in group number 2, how many valence electrons you have? 2 valence electrons you have, okay? 2 valence electrons. How many valence electrons you have? 2 valence electrons, right? Now tell me, in BeCl2, how many bonds it can form? I am just randomly writing it. 2 bonds it can form. So beryllium had 2 valence electrons, and we know only valence electrons can participate in the bond formation, right? 2 valence electrons are occupied and 2 valence electrons are busy in making bonds. So that means there is no lone pair here. So can I say 2 valence electron minus 2, because 2 bonds are already, it is forming 2 bonds, 2 bonds, bond pairs. You can say 2 bonding electrons, bonding, or you can say bond pair electrons. From beryllium, 2 bond pair electrons you have, and the valence electrons are also 2. That means there is no lone pair. Can I say there is no lone pair? If there is no lone pair, that means here you are going to have only 2, right? Here you are going to have only 2. and this 2 corresponds to SP. That will be linear geometry. Right? And that's how we can say that it is having a linear geometry. Right? Okay, because we know that whenever you have number of electron pairs are 2, that means it is going to have a linear geometry. Right? Now I am not teaching you with the help of steric number, I am teaching you with directly from the electron pairs, because calculating steric number is a long method. Maybe now you will feel, ma'am, even this is long, but when you practice, it will be like within seconds you will be able to answer, okay? So what you have to do, even if I just erase all of this, what you need to know, beryllium belongs to group number 2. It will have 2 valence electrons. And will it have any lone pair? There will be no lone pair. That means bond pair, you can say bond pair plus lone pair. Bond pair is 2, lone pair is 0. So bond pair plus lone pair is 2 only. So that's why it is a linear geometry. Bond pair plus lone pair is nothing but that is steric number only. It's just that way of answering steric number is changed. I'll show you some more examples here. Let's talk about BF3. Okay, BF3 is boron. Boron belongs to, don't write the electronic configuration. Even if you know that which group it belongs to, then also you can answer. Now boron belongs to group number 13. It belongs to group number 13. It will have 3 valence electrons. 3 valence electrons. And if I write down that in BF3 it must form 3 bonds. It will be like this. Right now I have no idea what will be the structure. I am just saying that it must form 3 bonds. Now boron had 3 valence electrons, and those 3 valence electrons are already occupied in making 3 bond pair electrons are already there. So that means there will be no lone pair. 0 lone pair you will have. So that means you can say lone pair plus bond pair is nothing but that is 3 plus 0, that is 3. That belongs to sp2 hybridization, that is nothing but it is trigonal planar. It is nothing but it is trigonal planar. Okay, so that's how you are going to answer this. Is that clear to everybody or not? Is that clear how we are going to answer this? Right, it is sp2. Now what is an sp2 trigonal planar? If you see linear geometry that we discussed here is sp, that is going to look like this. This is a linear geometry, right? Linear geometry, that is 180-degree angle. In a trigonal planar structure, you will have this kind of structure where it is in a plane and it is like a triangle you have, right? And if you divide 360 by 3, you will have 120. So that means each angle is going to be 120 degrees here, right? Okay, now next is example I'll take. Let's take the example, let's say CH4. Okay, let's say CH4. Now in CH4 what you have? In CH4 what you have? Carbon belongs to group number, which group? 14. Group number 14 means it will have 4 valence electrons. Valence electrons will be 4. And if you draw here, it is CH4, that means it is going to be H, right? 4 valence electron you had here, and all 4 electrons are busy in making the bonds. That means 4 minus 4 bond pair electrons, all of them are busy in making bond pairs. So that means there will be no lone pair, So we can say bond pair plus lone pair. Bond pair plus lone pair. That is going to be equals to 4 plus 0, that is 4. Because how many bonds it is forming? It is forming 4 bonds, right? So that is going to be equals to 4. and 4 means that you are going to have, and here whenever I am telling you bond pairs, that means I am talking about the sigma bond pairs, okay. So it is going to be sp3, and that means it is going to be tetrahedral geometry. It is going to be tetrahedral geometry. Now tetrahedral geometry looks like this, okay. This is a tetrahedral geometry, as you can see this here. This is a tetrahedral geometry, right? Okay. So now all the angles are same, because when I am rotating it, it is giving me the same structure, right? So this is going to be 109 degrees, right? 5 minutes. 109 degrees, and all the angles are same as I have shown you, right? Next is PCL5. It's a very, very important structure, right? If I talk about PCL5, right? Phosphorus, that belongs to group number 15. It will have 5 valence electrons. 5 valence electrons. And if you see the bonds that it is making is PCL5, that means there will be no lone pair. All the 5 valence electrons are busy in making bonds. So that means there is no lone pair, no lone pair, no lone pair, because these 5 valence electrons are making, these are making bonds, these are making bonds. So that is the reason there is no lone pair, and hence what you will have here, you will have here bond pair plus lone pair, that is going to be 5 plus 0, that is 5, that is nothing but sp3d, that we call trigonal bipyramidal. Trigonal bipyramidal, okay. And trigonal bipyramidal is actually this kind of geometry. And here what we are talking about is geometry, okay. I'll tell you what is the difference between shapes and geometry. So you have a trigonal planar. In that trigonal planar, you will have at 90 degree, you will put 1 upwards and 1 atom downwards, and these are the 2 pyramids. First is this pyramid, then there is this pyramid. These are the 2 pyramids that it is forming, and that's why it is called as trigonal bipyramidal, because it is having 2 pyramids here, okay, right. This is having 2 pyramids. This is trigonal, and this above and this below is pyramids, right. Okay, yes everybody. Now let's understand SF6. Sulfur, it belongs to which group? Sulfur belongs to group number 16. So group number 16 means how many valence electrons? 6 valence electrons, right? 6 valence electrons. How many bonds it is forming? SF6 means 6 valence electrons are occupied in forming bond pairs, right? They are busy, that means there will be no lone pair, there will be no lone pair. And guys, if I am saying that there is no lone pair, no lone pair if it is forming, that means bond pair plus lone pair is going to be 6 plus 0, that is nothing but 6. That is sp3d2, that belongs to octahedral geometry. That belongs to octahedral geometry. That looks like this. Okay, you have a square planar that we have discussed in coordination chemistry as well. If you don't know what is a square planar, in a planar you have a square kind of structure, that is square planar. Now in that, above you have 1 atom, below you have 1 atom, that is called as octahedral. Why this is called octahedral? Because it has 8 triangular faces, right? Let me just show you if we have anything where I can actually show you the triangular faces. This is the first triangular face, second triangular face, third triangular face, fourth face, fifth, sixth, seventh, and this is 8th. So each triangle, if you see, each one is making 8 triangular faces here. So that's why it is called as octahedral. Ma'am, can we also write number of electrons of that atom representing as X? We connect the surrounding atoms and we can write steric number by adding bond electrons and lone pair. Yes, IIT, you can definitely do that as well. Okay, whatever suits you. Right? There are various methods. It's not like methods are different. What you are doing is also the same thing. That's what I told you. You can calculate the steric number from also, that also you will get the same hybridization. In end, what you need to know, you should know what is a hybridization, what is a steric number. Whether you calculate it by this method, it's a, I prefer it as an easy method. Rest is totally your choice. Okay. Now, till now we have only discussed the structure. Can you see? No, everywhere we have no lone pair, so things were easy. I was not even talking about multiple bonds till now, right? But now we are going to proceed towards the multiple bonds. We are going to talk about lone pairs as well. So firstly, let's talk about lone pairs, okay? Each one will discuss the lone pair, right? Okay, yes. Now, if you see, I'll just show you this with the help of the structures that are given here. This one is SO2, wait a minute. This one is SO2 and O3. SO2, O3. Now first we will discuss about SO2, right? Let's understand that SO2, how it is coming out to be trigonal planar, right? If you talk about SO2, right, do we know one thing, that here you have sulfur that belongs to group number 16 and it has 6 valence electrons. It has 6 valence electrons, isn't it? Yes, it has 6 valence electrons, that we are clear about. Now, if it has 6 valence electrons, then see one thing, oxygen always wants to, do you know this thing, oxygen is very happy that it is forming 2 bonds. Oxygen is not happy in making 1 bond or 3 bonds, right? So here you have sulfur, right? To apply this now, you should have a little bit common sense also, okay? That definitely with oxygen, sulfur forms multiple bond, double bond, right? Because oxygen, if you draw it like this, oxygen is definitely not happy here. Then oxygen will have negative here and negative here. But it is not SO2O negative. It is SO2 simply, right? That means in that case, this oxygen and this oxygen should have double bond, right? Okay. Now, if I talk about this thing that sulfur should have multiple bonds, now let's see how do we find the lone pairs here. Okay, how do we find the lone pairs here? Sulfur, how many valence electron it has? 6 valence electrons. 1, 2, 3 and 4. Out of that, 4 valence electrons are already busy. 4 valence electrons are already busy in making bond pair electrons, already busy. 4 valence electrons of sulfur are making bond pairs, right? Can you see that? Yes. Now you have 2 electrons left here, and 2 electrons means you will have 1 lone pair, right? That means, can I say bond pair plus lone pair? You know, some students what the biggest mistake that they do. Bond pair, ma'am, 1, 2, 3, 4, ma'am, 4 plus, ma'am, 1, ma'am, 5, ma'am, sp3, ma'am, d. Trigonal bipyramidal, absolutely wrong, right? Why? Because what I told you, when you are writing here valence electrons, you will see the group. When you are writing here the bond pair electrons, you will see how many bonds it is forming. So it is forming 4 bonds. So you will subtract 4 here. But when you are calculating, writing here, then you will write the sigma bond pairs. And sigma bond pairs, that means 1 and 2. So here answer is going to be 2 plus 1, that is 3. That is nothing but it is sp2. So the structure is going to be trigonal planar structure. Trigonal planar structure. Understood, everybody? Yes, Sharath, write it down in the chat box. What is the doubt that you have, right? Bond pair. See, you can say bond electrons. Bond pair means this is, see, when you have a bond, right, the electrons that you write here are the bond pairs. Okay, so you know, if you are getting confused here, I am talking about the bond pair electrons from center metal atom, right? I am not considering oxygen here. We are only talking about sulfur. That sulfur, how many valence electron it has? Because sulfur belongs to group number 16, it has 6 valence electron, right? That is clear. Now, how many bonds it is forming? You can also write 4 bonds. 4 bonds. You can write 4 bonds. And how many sigma bonds? How many sigma bonds it is forming? It is forming 2 sigma bonds. So, how many bonds? You will subtract that. How many bonds? Sulfur, the center metal atom, is forming, right? Okay, understood? Now it is a trigonal planar, so we will reject this particular structure. The answer will be sulfur because it has one lone pair of electrons here. So it will have a trigonal planar geometry that will look like this. Okay, now a very interesting thing we are going to do, which I'll write here. What is the difference between geometry and shape? What is the difference between geometry and shape? Usually, I don't know why, but in JEE questions sometimes they replace, sometimes they ask geometry but they write shape, but the actual definition is that geometry is nothing but when we calculate lone pair plus bond pairs, right? We see both of them. But in shapes, we only see the bond pairs, only the bond pairs. I'll tell you how. Because earlier we didn't have any lone pairs, so that's why I was not telling you that, right? But now the geometry and shape will be different. This is the geometry. This is the geometry which we are saying bond pairs and lone pairs, that is coming out to be the geometry. But in shape, what you have to do? You have to ignore that, right? Okay, you have to ignore that. Now, this is the geometry, okay? So, when I am saying a lone pair here, let's imagine that this green atom is a lone pair, okay? So, now if you see, this is a trigonal planar geometry when you include the lone pair, but when you ignore the lone pair, isn't it bent V? Isn't it bent V shape, right? So that's why the shape here is bent V, okay? The shape here is bent V, bent V shape, okay? Got it, everybody? Yes, bond pair electrons and lone pairs and fine shape. Yes, Satin, you can do that, right? Okay, yes. Two bond pair plus lone pair, nahin. Two bond pair plus lone pair is angular shape, but there is some reason behind that. Now, firstly, you should know the geometry. What if they ask you the geometry? Don't learn these things. Don't cram that in 2 lone pair, 1 bond pair. Then you will get definitely confused. Just remember that whenever there is sp2, that is trigonal planar. Now imagine a trigonal planar. Now ignore the lone pair. What shape you have? You have a angular shape or bent V shape. So that is the answer. Okay, you don't have to learn these things. Okay, everybody. Thank you, Tanmay. Right. Okay, yes. Understood? With 0 lone pair, geometry and shape is same. Okay, when there is no lone pair, geometry and shape is going to be same. Right? Now that's why we had trigonal planar arrangement of bond pair and lone pairs, but the shape is bent V shape. The shape is bent V shape. Right? Okay? Now, let's understand NH3. Right? In NH3, what you have? Now, nitrogen belongs to, firstly you should know, nitrogen belongs to group number 15. So, it will have 5 valence electrons. 5 valence electrons. Now, can you say it is NH3? It is NH3. So, it is like this, right? That means it is only forming 3 bonds. So, that means out of those 5, only 3 are occupied. Valence minus number of bonds that it is forming is giving you 2 electrons. That means it is forming 1 lone pair. Because always 2 electrons form 1 lone pair, 4 electrons will form 2 lone pairs, right? So, 1 lone pair it will have. That means bond pair plus lone pair. Bond pair 3 bonds plus lone pair is 1. It is 4, that is sp3, right? So, you can say in reality the geometry is going to be nitrogen, this lone pair, and this is going to be a tetrahedral shape. In 3D we actually write it like this, but in 2D we draw it like this, but in 3D it is like this. This one is the above and these are the 3. 1, 2, 3. Can you see that? Like this. 1, 2 and 3. This is in 3D. Okay? This is in 3D how it exists. Right? Now, if you see, this is sp3, that is your tetrahedral shape or geometry. Tell me. Shape or geometry? Arey ma'am, this is geometry ma'am. We know ma'am. Now, who will tell me the shape here? Who will tell me the shape? Do you need to cram it? No, never, never, never. Okay? So, let's imagine that this green atom is giving you the lone pair, okay? And these other 3 are your bond pairs, okay? With nitrogen and hydrogen, okay? Right? Now, let's ignore this. Tell me what is this kind of shape? What is this shape? What is this shape? This is not trigonal planar. Now, one of you wrote it again, right? Right? Yes, 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 yes. Angular, 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 very good. Very good, very good, very good. Achha, did I say angular there also? I think by mistake I said angular there. It was bent V here, okay? It was bent V here. Bent V was this thing. This is bent V shape. What is V? V looks like this, no? So, it is bent V, like bent V shape, right? So, this one, if you can see here, this is, wait a minute, this is your, this one, can you see this here? Can you see this here? What kind of shape it is showing? Acha, tell me one thing. What is trigonal planar? I'll just show you that. Right? This one is planar. Okay? This one is planar. Right? Because it is on a plane. Same thing, it is on a plane. Right? This is my hand. You can see this. This is on a plane. Right? But if I see this here, is it on a plane? Is it on a plane? No. If I press it, it is not on a plane. It is not on a plane. It is not planar. So, it is a pyramidal structure. It is a pyramidal structure. Got it? So, what we'll write here? Trigonal pyramidal or simple pyramidal, you can say. That kind of structure it has. Right? So, answer will be pyramidal. Pyramidal. Okay? Next is you have H2. Now in H2, this is H2O. In H2O, what you will do? Same thing, okay? Same thing. Same thing we'll do here in H2O. This is H2O. Okay, tell me what is oxygen? Who will do this? Oxygen belongs to group 16. It has 6 valence electrons. Now, oxygen, this is oxygen centimetal atom, this is hydrogen. Let's not draw it like this. Let's draw the random structure here. We have no idea how many lone pairs whatsoever, right? So, let's see. 6 is the number of valence electrons, out of which 2 valence electrons are busy in making bonds, right? So, minus 2, it will be 4 electrons. That means it will be 2 lone pairs. Now bond pair plus lone pair. Sigma bond pair plus lone pair. Sigma bond pair is 2 plus lone pair is 2, that is 4. That means sp3. So I can say that here definitely tetrahedral is the geometry. But what about the shape? What about the shape? Who will tell me that? What about the shape here? Okay. So this was tetrahedral. 2 lone pairs if I need to draw, what I'll do? 2 lone pairs I'll draw here, right? Okay. Yes. Okay. Right. So 2 lone pairs I'll draw here, right? So can you see, if you don't ignore this is a tetrahedral geometry only when you focus on lone pairs as well. When you ignore the lone pairs, right, then what kind of shape it is giving you? Isn't it bent V shape? Isn't it bent V shape? Right? So can I say that is bent V? So I'll just write here bent V, okay? Write here bent V. Wait a minute. I'm confused in one thing. Angular. Was it bent V or was it triangular? Angle. It is making not pyramid. Yes, you are right. You are right. I just got confused there. This is only pyramidal. Yes, my bad. Right? Bent V is regarded as angular. Right. Bent V is regarded as angular or V shape or bent V shape. Okay. So that is your bent V. Very famous by bent V shape. Right? But if they ask you the geometry, that is going to be tetrahedral. Right? Now, next is SF4. Let's discuss SF4. Right? These are very famous structures. You will see this in your PYQs. Okay? Sulfur is group 16. Group 16 is 6 valence electrons. Right? Now, out of these 6 valence electrons, it is forming 4 fluorines. 4 fluorines you have here. Wait a minute. I need to draw the real structure here also. This will not be the real, this will be the real. Okay, bent we know, this will be the real structure. Okay. Now, this is the structure that we have drawn. 4 bond pairs it is forming. So 6 minus 4 means 2 electrons, means 1 lone pair. If it is 1 lone pair, that means bond pair plus lone pair is going to be 4 plus 1, that is 5. sp3d, that is trigonal bipyramidal. Okay, so geometry is going to be trigonal bipyramidal. And what is the shape going to be? The shape, if you see, it is going to have 1 lone pair here. It is going to be bipyramidal. So 1, 2. Now, where we actually need to put our lone pairs, right? Everybody, should I put the lone pair? See, these are the 3 positions. These are the different positions that you have. Now, anybody who will tell me where should I put the lone pair? So, for that is a very interesting concept of repulsions, right? Okay, we'll draw pH3 also. Okay, in the end I'll do that. Okay. Thank you so much, Latika. Thank you so much. Now, guys, if you talk about this here, right? There are two kinds of positions. One is axial position, other is equatorial position. Okay. So, what exactly we do? Firstly, we prefer first lone pair here, then second lone pair here, third lone pair here. This is how we prefer it. That means I'll tell you the reason here. What is the reason behind that? Okay, so I'll just show you the geometry. Just give me a second. Yes, here it is. right? I'll just show you the geometry here, okay? So if you see this here, right, what exactly happens? If you talk about these axial bonds, right? So in that case, what will happen here? So in these, which are in the trigonal planar phase, right, they have 120-degree angles, and here this one and this one has with this thing, this bond, wait a minute, this bond with this bond, they have 90-degree angle. This bond with this bond have 90-degree angle. This bond with this bond have 90-degree angle. That means if I put one lone pair here, okay, let's say this yellow is defining the lone pair, okay. So lone pair, bond pair repulsion, lone pair, bond pair, lone pair, bond pair. So you have 3 lone pair, bond pair repulsions, okay. Remember that we have 3 lone pair, bond pair repulsions here, right, when we put it. Now what I'll do, I'll just exchange it. What if you have your lone pair here? Now those lone pair bond pair were at 90 degrees. Now this lone pair bond pair is at 90 degree. This lone pair bond pair is at 90 degree. That means 2 lone pair bond pair is at 90 degree. Rest it is 120 degree angle. This lone pair bond pair is at 120 degree. This lone pair bond pair is at 120 degree. Right? And that is the reason this particular bond is preferred, because 90-degree lone pair bond pair repulsions are less here. Okay? Yes, everybody? Okay, everybody do let me know in the chat box. Everybody in the chat box. Is that clear? Is that clear? So can I say that it will always prefer equatorial positions? If I draw here, if I just write here, lone pairs are preferred at equatorial. These positions that can move, these trigonal planar positions are equatorial positions, right? And this one is your axial position, okay? So preferred at equatorial positions. Equatorial positions. Okay? Lone pairs are preferred at equatorial positions so that they can make a bond here, right? So they are preferred at equatorial positions, right? Now guys, let's draw the structure, let's draw the shape, okay? So if I tell you here, I don't have to place it here. Now let's see, the lone pair will be on the equatorial position. And now some students also ask me, ma'am, should I put lone pair here, or ma'am, should I put lone pair here, or ma'am, should I put lone pair here? Is that a question in your head as well? Where should we put, or you're clear on that? Right? See this in 3D. Even this is a structure that you can see, right? Now I'll exchange the positions. Okay? Now I'll exchange the positions. It was earlier this thing. Now I'll just rotate it. Isn't it the same? Okay, let's change the positions again. Right? Let's change the positions again. Now, I should rotate it, it will have the same thing. That means all these are same. Even if you put it here or here or here or here, that is the same. Right? Just in 2D we write it like this. It's just that in 2D we write it like this, that here you will have a lone pair and rest of them will be yours, so that you can visualize that this is a seesaw position. This is a seesaw shape. So how do you visualize it? What is a seesaw shape? Just ignore the lone pair. Can you see this is like a seesaw, right? Have you ever taken seesaw? Right? Seesaw, seesaw. This is you and this is your friend, right? Seesaw position this is, right? So that's why This is called as seesaw. Okay, this is called as seesaw shape, a very famous shape. Okay, right? Have same hybridization but different shape and bond angle. Yes, definitely right, IITian, definitely. They have same hybridization but they have different bond angles. Why the bond angles are different? Because of these lone pair. Wait a minute, let me just show you that as well, right? I forgot to show you the angles here. What will happen? You know, actually what will happen here? If you talk about, where should I show you the angles? I'll just show you here, okay? If I talk about CH4, this will be CH4, right? NH3 is like this. All of them have sp3 hybridization, right? Then you have H2O like this. Have we discussed that lone pair repulsions are maximum? Here you have bond pair repulsion, so angle is 109, okay, 109 degrees. Here you have lone pair repulsion. So you know what is going to happen here? You know what is going to happen here? Everybody, do you know what is going to happen? See, yes. So let's say you have a lone pair here, right? So this lone pair is going to repel this one, lone pair is going to repel this one, lone pair is going to repel this one, because lone pair bond pair repulsions are more than bond pair repulsions. Earlier you had here bond, right, bond. So that's why they were less. But lone pair, because they are free electrons, unpaired electrons, not unpaired but actually they are free electrons, right? So that's why they have an electron cloud which is more which can spread out more, right? So that's why these repulsions are more, and that is the reason this angle here will decrease, okay? This angle here will decrease, it will be around 107, right? So this angle will decrease here. If you talk about this angle here, this will even cause more repulsions here, even more repulsions, some 104 degrees it will be, right? Even more repulsions, these will repel here, lone pair and lone pair are with each other also, they are going to repel, okay, and they are going to decrease this angle here, and that will be around 104. In detail we'll talk about they are paired. In detail we'll talk about these bond angles in the next class, where we are going to discuss about various factors of bond angles, Drago's rule, everything we are going to discuss there, right? Okay. So next is we have not discussed this, CLF3, okay, CLF3. Let's discuss CLF3. Okay, everybody. So CLF3, how do we discuss that? Everybody in the chat box. CLF3, very good, very good. So who will tell me this? Chlorine you have, ma'am, yes. Chlorine belongs to group number 17. It has 7 valence electrons. When valence electrons are 7 and it is forming how many bonds? 3 bonds it is forming. Fluorine, fluorine and fluorine. So that means 7 minus 3, that is 5, 6, 7, 4 electrons. That is going to give you 2 lone pairs. 2 lone pairs it is going to give you. That means sigma bond pair plus lone pair is equals to bond pair is 3, lone pair is 2, that is going to be 5, that is going to be sp3d. Now who will tell me the geometry? Who will tell me the geometry? We have discussed this. Just now we discussed this. Geometry is going to be geometry is going to be trigonal bipyramidal. So it is going to be trigonal bipyramidal, okay, right? Now tell me one thing. For trigonal bipyramidal, it should have this kind of structure, 1, 2, 3, 4, 5. I should always place 2 lone pairs on the equatorial position, so I will place it here, right? So first and this is second, these are the lone pairs and these are the bond pairs. Now geometry is trigonal bipyramidal, that I can see, but how many lone pairs you have? 2. So let's place it here. 2 lone pairs on the equatorial positions you need to have. So that means this also bond pair will go. You'll have 2 lone pairs here on the trigonal bipyramidal. Isn't it trigonal bipyramidal? Yes. These 2 are the lone pairs. So for shape, you have to ignore the lone pairs, take it out. Now, what kind of structure that you have here? T shape, right? So that's why directly we write it that the shape is going to be, T shape. Okay, that is visible there as well. Okay, so it is going to be T shape, like this, T shape. Okay, yes everybody? Okay, very good, very good, very good. Let's do that, right? Let's do that. Next is BRF5. Let's discuss BRF5. So many compounds, no, we have. BRF5. So these are very famous, okay? In questions, it will be repeated again, right? So then I'll just show you that, okay, this was the structure there. So BR belongs to which group? Group number 17. So you can say group number 17. That means it will have 7 valence electrons. 7 valence electron, yes ma'am. Now how many bonds it is making? It is making 1, 2, 3, 4, 5. 1, 2, 3, 4. I have no idea what is the structure. I just know that it is making 5 bonds. So it is 7 minus 5, that is 2 electrons. That means there is 1 lone pair as well. 1 lone pair means sigma bond pair plus lone pair is going to be 5 plus 1, that is 6, that is octahedral. So can I write the geometry is going to be octahedral, right? So erase this, this is not, usually students, BRF5, usually students take trigonal bipyramidal, right? But in reality it is not. 1, 2, 3, 4, 5, 6. Now this is octahedral geometry, okay? Now this was octahedral geometry when you had no lone pairs. Now you need to have 1 lone pair, that means 1 bond pair we need to take out, okay? So this is the structure that you will have, right? So geometry will say octahedral only, but the shape is going to change. How it will change? This will be your bond pair. Any one of you in the chat box, write it down. Any one of you who knows what is the shape. I'll just give you a hint here. This is a square planar geometry and over there you have a pyramid. Now tell me what is the possible name? Yes, very good Supriya. That is square pyramidal, ma'am. This is the square that you had here, right? And over this you have a pyramid, okay? Ouch. This one is the pyramid, okay? So that is a pyramid. So you can say that it is a square pyramidal, not bipyramidal, only one pyramid you have. Pyramidal geometry. Okay? Yes. Now let's talk about multiple bonds, okay? Now if you see, these is multiple, this we have discussed, isn't it? Have we discussed SO2? Yes, we have discussed that. Achha, this is all we have discussed it, okay? We have discussed all of them. We have discussed all of them, okay? We have discussed all of them. Theoretically, the shape should have been trigonal planar, but actually it is found to be bent or V-shaped. Reason being lone pair bond pair repulsion is more as compared to bond pair repulsion. The angle is reduced to 119 from 120. Can you see there is a reduction of angle here? Right, let's talk about angles now. Let's talk about angles now. Where it was? It was trigonal planar, right? Wait a minute, let me just see that. It was trigonal planar. Let me just draw that, right? This was trigonal planar. Now when you have a lone pair here instead, because of that lone pair bond pair, lone pair bond pair, lone pair bond pair, lone pair bond pair repulsions, this angle, this 120 angle is going to decrease to 119 degrees. Okay, so that's why here the angle is 119 degrees. Okay, got it, right? Next is NH3. In NH3 also the angle has decreased. So here you had one lone pair. I'll just draw that lone pair here. So you had one lone pair here, right? Isn't it? One lone pair bond pair, lone pair bond pair, lone pair bond pair repulsion. The angle was supposed to be 109 degree, but now it has reduced to 107 degree because of, again, lone pair bond pair repulsions. Now if you talk about H2O, we'll have two lone pairs. So even now you will have lone pair repulsions as well, right? Now the thing has even changed, right? You will have lone pair repulsions. So these two will repel each other, these will further will be repelled, and they will further cause lone pair bond pair repulsion to a greater extent, and this angle, which was supposed to be 109, is going to get decreased to 104 degrees. As you can see this here, 104.5 degrees, right? Okay, so that is how lone pair bond pair is going, these repulsions, this is actually VSEPR theory. Okay, so how this VSEPR theory is applied when you have lone pair bond pair bond pair repulsions. Okay, right everybody? Now here also we discuss that why not here, why this is the wrong structure and this is the correct one, because on the equatorial position the repulsions are less, right? Okay, shown is described as distorted tetrahedron, a folded square or a seesaw. What are the names? A folded square or a tetrahedron, distorted tetrahedron, folded square or a seesaw, right? Okay, now in CLF2 also you had this place also which is wrong, this place also which is wrong, right? You need to have both the lone pairs on the equatorial positions, right? So that the repulsions are least here, right? And on the axial positions, right, as it is written here, compared to others in which lone pair are at axial position where repulsions will be very high. At equatorial positions, the repulsions are very less. Got it? Yes, everybody. Now let's do some questions based on that. Trifluoromethyl free radical CF3. Okay. I think that will be here only. ITN, right? Okay. CF3 because it's fluorine is more electronegative, no, right? So that is the reason. If you talk about CF3, this one you're talking about a free radical, na? Huh. So in that I'll tell you what exactly happens. Where should I tell you that? Wait a minute. It's a very interesting point here. Very good. So I'll just write it here. You have two things, okay? This is CH3 free radical. This is CF3 free radical. So there is a, whenever you calculate the steric number, when you calculate the steric number, we calculate it by bond pair, sigma bond pair plus lone pair, right? In this case, whenever you have less electronegative across the centimetal atom, you have less, it is attached to less electronegative. This free radical, you will not consider it as a lone pair, right? So that's why it will be 3 only, right? It will be sp2. But here, you will consider this as sigma, and 1, this free radical is considered as the lone pair, and it will be sp3. Okay? Yes, everybody? Yes. Got it? Yes, students? Wait a minute. Let me see if I can find a question for you here. They asked in my mock test. Now tell me, is that clear? Right? IITN, is that clear? IITN, what's your name? Yeah, Riya, is it? Yes, 119. What is 119? Understood now? I'll just write it here. If sentimental atom, free radical is attached to less electronegative, then it is considered as, then we can then free radical will be ignored, will not take part in hybridization, okay. But if sentimental atom is attached to more electronegative, like here it is attached to more electronegative, like fluorine, more electronegative, then free radical will be taken as lone pair. Free radical will be taken as lone pair. This is by convention, we take it like this. Okay? So that is the reason here it is sp2 hybridized. That means it will be one trigonal planar. It's like this, and here you will have a free radical, right, like this, which is not a part of the shape, right? But here it is 1, 2, 3. It is a pyramidal shape. Here this is going to be this is actually like a free radical. This is behaving like a lone pair only, right? So this is your pyramidal shape. Okay, and this one is trigonal planar. Very important question actually it is. Okay, it is a trigonal bipyramidal, it's a trigonal planar, and students can easily do mistake here, right? Okay, Sukesh, clear? Yes, everybody, shall we move ahead? Now let's do the questions of JEE Mains 2025, and JEE Mains previous year question only. You will find a lot of questions. Okay, so here it is, the molecules having square pyramidal geometry are which of the following? Let's see, the molecules having square pyramidal geometry are which of the following? Square pyramidal means they should have 6 as the square pyramidal. You already should remember that here steric number should be 6. Now you will say, ma'am, you know, this is a mistake that, not mistake, I would say this is actually in most of the exams, geometry and shapes are interchangeable words, but in exactly geometry is lone pair plus bond pair and shape is only bond pairs. This is the definition, but yes, they sometimes like things like this. Sometimes they will ask you the shape, but in reality the options will be like geometry. For that you need to apply common sense here. So we know that square pyramidal geometry does not exist. Geometry is octahedral, but shape exists. If you have octahedral geometry and you have one lone pair, one bond pair, let's say 5 bond pair plus one lone pair, then that can be the answer. So PCl5 is definitely not. So these two options are eliminated. BRF5 is definitely yes. Right? Now let's talk about these two. Let's talk about, firstly let's talk about XCO4. If this is not correct, it's not possible. See, if you apply common sense, if this is also not correct, then this will also not correct. Then that means all the options are not wrong. That cannot be true. We are confident that BRF5 is correct, right? That means C will be the correct answer. But still, let's find out for XCOF4, okay? So here if you see, xenon is group number 18, 8 valence electrons. How many bonds it is forming? Xenon, if you see, it will form 1, 2, 3, 4 bonds with fluorine and double bond with oxygen, because oxygen forms double bond, okay? So, very good, it is possible, right? Very good. So, bond pairs, how much it is forming? Bond pair it is forming. Whenever you are calculating that how many bond pairs it is forming, you need to subtract it from the valence electrons. You will calculate the pi bonds as well, right? So it is 1, 2, 3, 4, 5, 6, because this xenon is using its valence electron in pi bond as well, right? So that means 8 minus 6 is 2 electrons, that is 1 lone pair. If lone pair is 1, that means bond pair plus lone pair, that is going to be, bond pair is what? How many sigma bond pairs you have? 1, 2, 3, 4, 5. Lone pair is 1, that is going to be 6, right? Definitely this is what we wanted, na? Octahedral shape, right? One bond pair, that means xenon is going to be like this, isn't it? Yes, right? Wait a minute. Double bond O, okay? That is going to be the answer, right? So that means C is the correct answer here. Right, everybody? Got it? Okay. Now, all the structures are given to you. Most of them we have already discussed. If you talk about SB, right? That also you can easily calculate, right? Okay. Right now, is it a difficult task to calculate this? Can you do this? Do you need to do this? Chalo, let's do how you will calculate. SBF5. Okay, simple way is SB belongs to group number 15. Na, P, SE, Sharab, Bhai. Right, SB belongs to group number 15. So it is having 5 valence electron. Out of that 5 bonds it is making, it is having no lone pair. That means steric number is going to be 5, bond pair plus lone pair is going to be 5, that means it is sp3d, that means it is trigonal planar geometry, right? And this will be your, this is actually, they are showing the, let me show you that, they are showing inward outwards, okay, right, inwards outwards, right? They are showing that here. If you talk about that, this is this kind of plane. If I say this is the plane, this is my hand and this is the plane, okay? This is my hand and this is the plane. So this particular is solid wedge, it is outwards, or you can say it is forward, and this one is backward, so it is dash wedge. Okay, that's how they are representing this in TD. Okay. Ma'am, PH3, okay. So I'll do PH3, but this is the last one that I'm doing, okay? After that, you will not ask for any other shape, okay? Because in questions also, 3-4 questions also we have here, right? I thought today we'll do MOT also, but I really doubt it, right? So I'll see. I am already so tired. Let's see if I can pull it off or not. If you can also pull it off or not, right? Okay, very good. So pH3, what you have, phosphorus, belongs to group number 15. It has 5 valence electrons, right? Out of these 5 valence electrons, 3 are occupied in bond pairs. You have 2 electrons, that means 1 lone pair. Wait a minute. Is it 1? Yes, it is 1 lone pair, right? So here what you will have, this will be bond pair plus lone pair. It is going to be 3 plus 1, that is 4, sp3, that is tetrahedron, right? That is the geometry, right? It is like NH3 only, no? Right? Shape is going to be pyramidal. Okay? Okay. Yes, everybody. Yes, everybody. Let me know if that is clear or not. Let me know if that is clear or not. Right? Okay, students. Right? Ma'am, molecular orbital theory. I'll teach. Don't worry. Right? Don't worry. I'm going nowhere. Clear, everyone? Perfecto. Done. Yes. Okay. Pure orbital, so how can it have hybridization and has S sigma sp? Okay, I think you are getting confused. Okay, I think you are getting confused there. In bond angle concept you are getting confused, no? Drago's rule, I think. So, Sukesh, are you getting confused there? Don't worry, I'll talk about that. In the next lecture, I'll talk about that. But actually the shape is this only. Okay, this is the shape. Right? Okay, thank you so much. Thank you so much, Anjali. Ma'am, what about MOD? I'll teach you that. I am going nowhere. I'm going nowhere. If not today, I'll teach you tomorrow. I'll take extra class on Monday. My target is that within 2-3 days, I have to finish this, right? Because next Wednesday, I am starting GOC. That means I am starting GOC, right? So if I have taken that responsibility, you can definitely trust me, right? Okay? Yes, everybody? Chalo. Now, let's do, right? Yes. Sukesh, I know that. Don't worry, when I'll talk about Drago's rule now in the next lecture or maybe next to next lecture, if I don't complete MOT today, then I'll take it on the next to next lecture. I'll definitely talk about NH3 and pH3, all the orbitals, what is the reason behind that and why the shape is like this. Okay? Right? Okay. Yes. don't worry. Okay? As of now, you just remember that it is having pyramidal shape. It is having pyramidal shape. We'll talk about this in Drago's rule, that how NH3 and PH3. See, I don't want to disclose it here. That's why I was not picking a PH3 here, right? Because it will create more questions in students' head, right? And they will be like, ma'am, now we are again confused. So this is one of the exception that we are going to study from Drago's rule, but the shape is pyramidal only. The shape is pyramidal only, right? That I'll tell you there that how come shape is pyramidal, but now you just understand from this method. Then I'm going to prove this thing wrong, right? But as of now, just remember that it has a pyramidal shape. In Drago's rule, we'll talk about that why, what will be the hybridization, will there be hybridization or not, will there be no hybridization in PH3, but still how can the shape be pyramidal only? Shape will be pyramidal, okay? Right? Shape will be pyramidal, right? That is true. Hybridization will not be there, that is also true, but for now, just remember this. When I'll talk about Drago's rule, same page I'll take out and tell you what are the alterations that we need to do here, okay? Yes, everybody? Okay. How long the session is going to be, how much you want. If you want me to teach you for 1 more hour for MOT, I can do that. If you want, ma'am, please take MOT in the next class, I'll take MOT in the next class, that is tomorrow, and I'll take one extra class on Monday for bond angle and dipole moment. I can do that as well, right? Okay, or I can take lengthy class tomorrow, or what I can do, I can start MOT today, right? Like the initial part of that, and we can complete MOT in the next class, like questions and electronic configuration, everything we can do in the next class. So now let's understand this. Here see, they have asked you choose the correct answer. NH3 is what? NH3 is, see now can you see B, NH3 is actually trigonal bipyramidal, so this will be A. So PCl5 is trigonal bipyramidal, this will be C. B, wait a minute, not PCl, wait a minute. BRF5 is square pyramidal, yes, this is B, and trigonal bipyramidal is C. This all we have discussed. CH4 is tetrahedral, that is D, okay, all we have discussed. This is your JEE Mains 2025 question, okay. So this will be 1B, 1B, okay. I think B will be the correct answer. A3, A is 3, D is 2. A is 3, D is 2, C is 4, yes. C is 4, yes. So answer will be B is the correct answer here, okay. Now next question here, who will answer me this, who will answer me this, who will answer, I will not answer, you answer, okay, you answer, let me see. Should I put a quiz here? Should I put a quiz here? Okay, let's do that. Okay, I'll just make a quiz here. Let's see if you can answer that or not. How do I make a poll? Wait a minute. Okay, already there is a poll. So let me just start a new poll here, right? I'm not writing any question here, just answer A, B, C. That's why I love Sigma batch, because their quiz taking is so easy. Now I'm in a habit of taking quizzes, because in Sigma batch, this is what we do, right? Because quizzes is what makes students realize that like what percentage are able to answer correct answers, who are not answering the correct answers. So we have done all of them, we have just not done BRO3 negative, right? Okay, that I'll tell you how to do that, okay? If you're confused that ma'am, how do I do that? I'll tell you how to do that, right? Firstly, answer me by hit and trial also, you can answer me. Acha, I forgot to give you this. Okay. I forgot to mention that what is A, B, C, D, right? So now you need to answer me what is A, what is B, what is C, what is D, right? So firstly write it from here, match the following answers here, A, B, C, D, match the following answers here, right? Then answer it. So A, we know it is seesaw. So A is 3. A is 3, A is 3, C and D is already eliminated. Now you need to tell me whether B will be 4 or 2. From there you can answer. BRF3, this also we know that this is square pyramidal. BRF3, it is BRF3, okay, it is not BRF5. That is going to be different. So see, this is, if you see, BRF3, group number 17 means 7 valence electron minus 3, 4 electrons means 2 lone pair. So 3 bond pair plus 2 lone pair is 5, and here you will have this kind of structure where you will have 2 lone pairs. So it is definitely going to be a T shape, bent T. Why it is a bent T shape? Because this lone pair is going to cause repulsion, this lone pair is going to cause repulsion, so it will be a bent T shape. So I can say that B is 4th. So answer will be B is the correct answer. Now how C is BrO3 negative? BrO3 negative, I'll just draw it here, BrO3 negative. Guys, if you draw this here, what you will have, bromine belongs to group number 7 minus, now bromine will always have double bond, double bond, double bond. So it will minus 6 it will be, means, and we are going to add 1 also here, because a negative means it will gain 1 electron. So I am going to add 1 here. So it is going to be 7 minus 6, that is 1, 1 plus 1, that is 2. 2 electron means 1 lone pair will be there, right? So what we'll do here, right, this will be bond pair is how many bonds, sigma bonds, 3 bond pairs plus 1 lone pair, it is 4. So it is going to show you tetrahedral geometry, but shape is going to be, if you see this, tetrahedral, you have 1 lone pair, the shape is pyramidal. If this is also the, say this is also the bond pair only, that is a pyramidal geometry, isn't it? So pyramidal shape, so answer will be pyramidal shape. Pyramidal shape. Okay, so that's how you will have pyramidal shape here, right? Okay, BrO3 negative, that's how it is a pyramidal shape, right? And next one, last one, we already know that how it is going to be tetrahedral. NH3 with lone pairs, it is tetrahedral, okay? It is pyramidal. No, this is a pyramidal shape. See, this is a pyramidal shape. But when it donates these lone pair, this lone pair, when it is donated to hydrogen and it carries this positive charge here, right, that means it becomes like this, it donates this electrons here, then this becomes tetrahedral. Then the geometry and shape both will be tetrahedral, right? Okay, I'll do that. If you have asked for it, then we'll do that someday, right? Okay, we'll do that someday. In fact, I'll ask Shreyas sir and Namrata ma'am so that we can do quiz together also for PCM. I'll ask them, right? If you guys are interested in that, right? I'll conduct a poll today on the Telegram channel. If you guys are interested, if I feel like 200 votes there for the quiz, then definitely we will have a session where all of us, Namrata ma'am, me and Shreyas sir, we are going to take up questions for you, the chapters that we have completed till now, right? Okay, yes. Now, this is actually, this we can do in the next class, because here, you know, some concepts that we have not talked about till now, they are also here. So this we'll do in the next class, we'll do in the last class, okay? This will do in the last class. Yes, let's talk about shapes only today, right? Then you have ICL, ICL3, CLF5 and IF7. See, IF7 is a very famous compound, right? The thing is that because it forms 7. See, iodine belongs to halogen, it is group number 17. So 7 electrons. In 7 bonds it is forming, so there is no lone pair. For 7 bonds, till now we have discussed about 6 bonds, okay? We have not discussed about 7 bonds. If it is forming 7 bonds, that geometry is very famous. That is your pentagonal bipyramidal. Just like we have trigonal bipyramidal, right? This is a triangle and here you have one pyramid and one pyramid. Same way you will have, instead of a triangle, you will have a pentagon here and one pyramid below, right? So that is a pentagonal bipyramidal, which is for 7 bonds when it is making, right? So what about ICL? ICL is also very interesting here. Now this is having 7 valence electron, minus 1 is occupied in forming bond. So 6 electrons means you will have 3 lone pair. Lone pair is 3 means you will have sigma plus lone pair. Bond is 1, lone pair is 3, it is 4. So that means it is going to have 3 lone pairs and 1 bond pair. 3 lone pairs and 1 bond pair. So 3 lone pairs and 1 bond pair means this is I, 1, 2, 3 and 4. So it is going to have only 1. This is going to have a linear structure. Why? Because this is how it is going to be. If you talk about a tetrahedral shape, geometry, 3 lone pairs means 1 lone pair, 2 lone pair and 3rd lone pair. And you are left with only this, that is a linear, right? Others will be the lone pairs, right? So in shape we have to ignore that, right? So that's why this is having a linear shape, okay? That's why ICL3 is having a linear shape. Let's talk about, ICL is having a linear shape. Let's talk about ICL3. Again, iodine is having what, everybody? Iodine is having what? 7 valence electron, minus 3. 4 electron means 2 lone pair. So sigma bond pair plus lone pair, that is going to be 3 plus 2, that is 5, that is sp3d, that is trigonal bipyramidal only. So we can form it like this, I, 1, 2, 1, 2, 3. 2 lone pairs means it will be like this. Can you see what kind of shape it is forming? It is forming a bent T shape, okay? Or you can say T shape as well, right? Same thing. Sometimes it is specified as bent T, sometimes it is not specified, right? Then you have CLF5. Let's discuss about that. CLF5. Let's discuss about that. CLF5, guys. CLF5, CLF5, okay. Now if you see chlorine again, it belongs to group number 17, 7 valence electron, minus 5, 2 electrons, that means 1 lone pair, 1 lone pair. Sigma bond pair plus lone pair is going to be 5 plus 1, that is 6. That is sp3d2, that is an octahedral geometry. So we can say that this is Cl, this is 1, 2, 3, 4, 5, 6 and you are going to have 1 lone pair, that means this can be your lone pair and rest of them can be the bonds. So can I say this is a square pyramidal geometry, right? So that is also written here, square pyramidal, right? Guys, are you now confident that from this particular topic, you can see repeatedly questions are asked and you need to have a good hold over it, right? Are you confident? Are you sure that yes ma'am will do that, right? Okay. So answer you can tell here, right, by matching all of them, answer will be B, right? Okay, understood? So let's talk about, in the end, let's talk about this. So from VBT, hybridization, see basically in reality what happened, firstly there was VSEPR, right? We talked about the flow can be different, right? But you need to understand one thing, that VSEPR has given you lone pair, bond pair, bond pair, bond pair repulsions. You talked about the repulsions, right? VBT majorly talked about that how overlapping happens, right? And hybridization talk about that in overlapping hybridization is needed, right? So now overall concept we applied and we answered the question by mixing these three concepts. Now in the end the last theory was VBT, right? Now why there is need for MOT, right? Ma'am, we are able to solve the questions, right? Right? Okay, yes. Here I just deleted that. I deleted that. I can't undo that now. Everything I have written will be wasted. Don't worry, I'm going to take it that. Okay, I'll take that. So, could not explain the paramagnetic nature of O2. So, O2 is paramagnetic in nature, right? So, he was not able to explain why is some are paramagnetic, why it is not getting paired up, why O2 is paramagnetic, why there is unpaired electrons, right? According to VBT, O2 should have been diamagnetic in nature, right? Because electrons are paired up, right? They should have been diamagnetic. Could not explain inertness of N2. Why N2 is inert? Like in our atmosphere we have N2, right? But it is not reacting, right? So why it is inert? Then could not explain formation of coordinate covalent bond. Why coordinate covalent bonds are also formed? What is the reason behind that covalent bond? He was all able to explain, right? Now, majorly to solve the paramagnetic nature of oxygen, there was a new theory, that is MOT, that is called as molecular orbital theory. What is the name of that theory, everyone? What is the name of that theory, everyone? Okay, Jovish, I'll definitely take that. I'll definitely see. It always works like this, more the demand, more the supply, right? If you ask for something, we'll definitely do that for you, right? So, let's talk about molecular orbital theory. Molecular orbital theory is, for example, let's talk about, you have valence electrons, right? How these atomic orbitals combine to form molecular orbitals. Very unique concept, right? Let's talk about that. So in MOT, valence electrons are considered to be associated with all nuclei in a molecule, and the atomic orbitals combine to give molecular orbital. They said that majorly atomic orbitals, oxygen will have, for example, 2 oxygens you have, right? So both of them will have atomic orbitals, they will combine to give a molecular orbital, and that's how it's like MOT is the quantum number theory, quantum theory of chemical bonding. Like we discussed Bohr model, which was absolutely like top-notch model. After that we have to discuss quantum mechanical model as well, because it was even better. Similarly, you have MOT here, it explained more things, right? So first thing is, let's discuss the features here. What is atomic orbitals, how they form molecular orbitals, let's discuss about that. Main features are the electrons in the molecules are present in various molecular orbitals as electrons of atoms are present in the various atomic orbitals. Just like you have atomic orbitals, you have 1s, 2s, 2p, 3s, 3p, 3d. Similarly, you will have molecular orbitals and electrons will be present there, and we will also discuss the electronic configuration of molecular orbitals. That will go like this: sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. This is for molecular orbitals. For atomic orbitals, 1s, 2s, 2p, right? So they said when atomic orbitals combine, they make this kind of electronic configuration in which electrons are filled, right? Electrons and molecules are present in various molecular orbitals, right? Then atomic, now here can you see the electrons of molecules? He is not specifying that only valence electrons, all the electrons are there, will be filled in the molecular orbitals, all the electrons, right? The atomic orbitals of comparable energies, if you compare the energies and proper symmetry combine to form molecular orbital. So guys, if you remember, we have understood the concept of overlapping, right? In overlapping, what we discussed, that this is one atomic orbital, this is another atomic orbital, they will overlap. We discussed, let's say this is one atomic orbital, this is another atomic orbital, it will combine, like P and S will combine. We discussed that this is one atomic orbital, this is atomic orbital, they will combine. We discussed that one atomic orbital, another atomic orbital, they will overlap. This was the concept of overlapping. Now we are discussing they are forming a new orbital only, right? That we are saying that two atomic orbitals, when they combine, they will form molecular orbital. And it's not like 1s can combine with 2s or 1s can combine with 2p. Not possible, right? The atomic orbitals of comparable energies and proper symmetry, that means 1s will combine with 1s to give you molecular orbitals, 2s will combine with 2s, 3s will combine with 3s, 2p will combine with 2p. That is how it is going to work, right? Same energies it should be. Then next is that when an electron in an atomic orbital is influenced, so what will happen? Why they need to? Ma'am, what is the shape of a molecular orbital? We'll talk about that. I have just started. Have patience. We'll talk about that, right? Okay. I have just started. Today, I am not going to tell you about electronic configuration and all. I am just going to read out the postulates. We'll discuss how it is formed. That's it. Electronic configuration, examples, filling of electrons, questions we'll discuss in the next class, right? But to understand molecular orbital theory, you need so many things. We'll discuss about that, right? Okay, so that this time we can save, right? So that next lecture, I really wish that I want to complete this chapter tomorrow on Sunday because so many students are free. So it's better if I complete that tomorrow only, right? Because on Monday again your school starts and you get busy, right? So while an electron in the atomic orbital is influenced by one nucleus, in a molecular orbital it is influenced by two or more nuclei depending upon the number of atoms of the molecules. Right? How many? But in your syllabus, you don't have molecular orbital of CO3. You don't have that. You will only talk about O2, N2, CN, NO, these things. So, in your syllabus, you have up to this only, right? But as you talk about, let's talk about CO2. 3 atomic orbitals are combining. There's so many atomic orbitals because 3 atoms it has. They're combining to form so many molecular orbitals, right? So that is the reason that so many nuclei are going to affect it, right? This atomic orbital is monocentric while molecular orbital is polycentric, right? It will have so many centers. Atomic orbital is only one center because it is only one orbital, right? Then the number of molecular orbital form is equals to number of combining atomic orbitals, right? Let's say 1s and 1s is combined. This is what you have in your syllabus. You don't have 3 atomic orbitals combining together. You have only 2 atomic orbitals combining together, right? So we'll stick to that only, right? Let's not get confused. 1s and 1s, that will give you sigma 1s and sigma star 1s. This is what is written here, that two atomic orbitals will combine to give you two molecular orbitals. One is your bonding molecular orbital, that is represented like this. This is BMO. And other is anti-bonding molecular orbital, that is represented by ABMO. ABMO. Okay? Just like in a school you have principal, vice principal, right? Similarly, you have anti-bonding, you have bonding, right? Now, two atomic orbitals are combining to give you two molecular orbitals, and one will be higher in energy, one will be lower in energy. Let's talk about that. The bonding molecular orbital has lower energy. That means it is more stability. So, what is happening here? This is 1s. This is 1s. It is combining. It is giving you two and molecular orbital. This is your bonding molecular orbital. This is your anti-bonding molecular orbital. Is it clear in your head, everybody? Right? Bonding molecular orbital, anti-bonding molecular orbital. Right? So, this bonding molecular orbital is always lower in energy, higher in stability. Anti-bonding, for example, the sigma, this is 1s, 1s, so this will be sigma 1s, sorry, sigma star 1s, this will be sigma 1s. In anti-bonding, it is represented by this star. Bonding, there is no star. Okay? Right? Akarsh, I have already done coordination chemistry. If you want to find the one shot of that, you will also find that on this channel. But as this channel is a pure English channel, so that's why I have taught it only in English, right? Okay? And my English is not that hi-fi, don't worry, you'll be able to understand that. Even my English is not that good, right? So don't worry. You will easily be able to understand English, what I speak, right? I don't speak very hi-fi vocab. That you'll be like, what ma'am? Firstly, ma'am, should I understand chemistry or should I understand your English? That confusion will not be there, right? Okay? So yes, my English is also like English, don't worry. So next is just an electron probability. Just as the electron probability distribution around the nucleus in an atom is given by atomic orbital, the electron probability distribution around a group of nuclei is given by molecular orbital. So simple thing is, he is saying that just like for 1s we say it is spherical. This is how the electrons are distributed. 2p is like this, right? Now it is given by electron probability distribution. Similarly, for molecular orbital also you have this wave functions, and these wave functions that we have discussed in structure of atom, we discussed about atomic orbitals, that these wave functions are going to give you that where the electrons are located, whether it's spherical or it's a p orbital, it's a dumbbell shape, it's a double dumbbell shape, what kind of shape it has, right? That we already discussed about, right? So similarly, in this case, in molecular orbitals also you have this psi, which is going to tell you the molecular orbital distribution of electrons, right? So the molecular orbitals like atomic orbitals are filled. That means these molecular orbitals are same as atomic. It's just that they are of two types, anti-bonding and bonding, and they are made by combining the atomic orbitals, right, are filled in accordance with off-bow principle. Now when you fill the electrons here, it is filled in accordance with the off-bow principle. What is off-bow principle? Electrons are filled in increasing order of energy. Lower orbitals will be filled firstly. Pauli exclusion means in one molecular orbital only two electrons of opposite spin. That is your Pauli exclusion. Hund's law means, firstly, degenerate orbitals are singly filled. First you will singly filled all the orbitals. Then see, ma'am, what you are saying, ma'am? We don't understand, ma'am. Let's see. I'll just tell you one simple example, right? We'll do the full-fledged diagram, don't worry. Right? This is 1s, this is 1s, this is sigma, sigma, this is sigma star 1s, this is sigma, sigma 1s, okay? So, if you, let's say, here also you have 2 electrons, here also you had 2 electrons, okay? So, they are combining to form these 2 orbitals. Now, how you will fill the molecular orbital? Firstly, this is at lower energy, so this you will fill here. Then because degeneracy is not there with any other orbitals, you will fill here. Then you will fill this one and this one. Okay? Understood? Now, let's talk more about these orbitals. Bonding, anti-bonding, let's talk about them more, right? If you are having fever, then go and relax, right? Your brain cells need rest. Right? Don't be so hard on yourself, right? Your body also needs rest. When you need rest, take rest so that your body can recover. Yeah, don't trouble your body so much. Don't do that, right? So, bonding molecular orbital, anti-bonding molecular orbital. If you talk about bonding molecular orbital, as we discussed, it's low in energy, high stability, involved in bond formation, right? Anti-bonding is high energy, low stability and is not involved in the bond formation, right? Okay, this is not involved in the bond formation. Yes, very good, Sukesh. We are going to do that. Very good. You're so excited. Ma'am, I know this, ma'am. Please, ma'am, listen to me. I know this. Right? I can hear your noises. Right? I know that you know this. Very good. So, let's talk about these things one by one, okay? So, just like I told you, this is atomic orbital, this is atomic orbital, right? Let's say here you have 1 electron, here you have 1 electron, okay? Let's understand, here you have 1 electron, here you have 1 electron. Now, first thing is these 2 electron has to be of opposite spin. If this is upwards, this has to be downwards. This will be downwards only. It is forming this bonding molecular orbital, this anti-bonding molecular orbital. So, together here you have 2 electrons in 1s, right? So, how it will be filled? 1, 2 and here this will remain empty. Why? Because here in total you had 2 electrons and according to Hund's law, or you can say according to Hund's law plus off-board plus Pauli exclusion principle, degenerate orbitals first will be singly filled, then they will be fully filled, then only you can jump to the next higher energy orbitals. Okay, right? Understood? So that's why here you will have 2 electrons here. Now let's say condition for this linear combination of atomic orbitals. As you can see, this I am representing by sigma A plus sigma B. This is sigma I am saying psi A plus psi B. Okay, this is represented by psi A minus psi B. So, what is exactly this? This concept is called linear combination of atomic orbitals. What is this called? Linear combination of atomic orbitals. Now, if I talk about linear combination, how does this happen? Let's talk about everything here. So, linear combination of atomic orbitals has 3 conditions. First is same and nearly same energy, right? Second is maximum overlap of combining atomic orbitals. They should have maximum overlap. Third is same symmetry about the axis. Now I know that this is going above your head. For that, let's see the diagrams, okay? Let's see the diagrams. Wait a minute. This will do, but for that, yes. Firstly, let me tell you the physical significance of MOs, okay? So that you are, so let's do the questions only. With the help of questions, let's understand, okay? With the help of questions, you'll understand it better, right? Let's do. These three conditions you have, with the help of questions, we'll understand it, okay? How actually it happens. So JEE 2025 question, that is based on the molecular orbital but not the electronic configuration. It's a general question that they are asking you, right? Which of the following linear combination of atomic orbital will lead to formation of molecular orbitals in homonuclear diatomic molecular internuclear axis in Z direction? Okay. So for that, one by one, we need to see how they are going to form the orbitals, right? So first, if you see, this is PZ and this is PX. Now PZ and PX, this is PZ, this is PX. So what I told you here, the condition is same or nearly same energy, maximum overlap, same symmetry, right? Okay. So if you talk about, PZ here and PX, can you see that maximum overlap is not possible? With PZ and PX, overlap is not possible. So because of that overlap, because overlap is not possible, that's why no molecular orbital will be formed, right? Okay? Because there is no overlap, so that's why molecular orbital will not be formed. Let's talk about S and let's talk about PS. Now they are saying that if you talk about this is PX and this is S. S is a spherical orbital. And can you see they are saying that you should have the overlapping along the z-axis, okay? Along the z-axis you should have the overlapping, right? If they don't say that it should be along the z-axis, then you can say, ma'am, this is x-axis. Let's say this is x-axis. So you can have spherical orbital here. They can combine together to form a molecular orbital. It is possible, right? But now, if you say this is actually given to be 2s and 2px, right? So first thing is the energy is not exactly same, right? But it is nearly same. But in this case, the thing is that if I say this is z-axis, so they are saying along z-axis you should have the overlap. So if I put this here, if I put this sphere over here, this sphere over here, this is not overlapping, right? Overlapping should be over here or here, which will be along x-axis. That will not be along z-axis. To have z-axis, it should be here. This will overlap here. So again, it is not getting overlapped, so it is not forming any molecular orbital, right? Okay. Now, third one is dxy and dx square minus y square. So, dx square minus y square is having the same energy same, okay? Now, along z-axis you need to have it. So let's say this is y and this will be z-axis and this is x and this is z. Wait a minute. This is, wait a minute, this will not be z, x square minus y square, this is also y, okay? This is also y. This is also y. First thing is, if you see, if you want to form a molecular orbital here, right, energy is same, that's fine, but they are not going to form any bond here because they are not going to have any molecular orbital here because this is between the axis, this is along the axis, right? If you're saying that it should be along the z-axis, and z-axis is this one. This is your z-axis and this is your z-axis. I'll just draw it. I'll just try to show you this in 3D. This is z-axis and this is also z-axis. These two are your z-axis. If these are the z-axis, if I am saying that these are the z-axis, then how can I make, because this is between x and y, right? This is between x and y you have. This is along x and along y. So how can along z-axis they can overlap? It's not possible only, right? So internuclear axes are z, it is not going to overlap there. And now last D is 2s and 2pz. So if you talk about 2s and 2pz, this is 2s and this is 2pz. Along z-axis you have to make it overlap. So if I say this is also z-axis, this is also z-axis. So now along z-axis, because along z-axis it needs to combine, so this can combine here, this can overlap here, and that is along the z-axis only, so that means this is possible, right? That means this thing is possible here, right? So we can say now, ma'am, what is this, ma'am? Now let's see that. This is overall positive. Let's say this is also, because they are going to form two orbitals, okay? It will be sigma A plus sigma B, or sigma, I am saying psi A plus psi B, or psi A minus psi B. So when they are overlapping to form a constructive, like that means positive and positive, this I told you in overlapping concept as well. When in phase overlapping is happening, when out of phase overlapping is happening, right? So in phase they will combine and they will make a positive overall, right? And this will be the negative side. This will be the negative side. Okay? So that is how sigma molecular orbital is going to form here, right? Okay? In E, what you have, let's see what kind of E you have. 2pz and 3x square minus y square. See, in this is 2px and this is dz square, x square minus y square. First thing is the energy, right, is not similar here. 2p and 3d energy is not similar. Second thing is, it is not possible because of internuclear axes are z. For this to combine here, here z is this one, here z is this one. So how can they overlap, right? If this is z, if it is overlapping like this, for example, this is the orbital, this is the z axis, and here this 2pz is coming from this side. So how can it overlap with those orbitals, right? So internuclear axes are only different, so that's why this is also not possible, right? Are you able to imagine that, everybody? So answer will be only in D there is a possibility. This is 2025 question which is entirely based on common sense and imagination, right? Simple concept was there. You should know all the shapes. You should know whether along internuclear z axis it will overlap or not, right? Okay. Okay, everybody, clear? No, I saw it, Suresh, I saw it, right? Okay, everybody, now let's see physical significance. Physical significance of MOs, let's talk about that. Molecular orbitals have definite energy levels, right? And their shape depends upon the shape of combining atomic orbitals. Now, what is the significance, right? So, molecular orbitals have definite energy levels, like you have sigma 1s, sigma star 1s, sigma 2s, right? And their shape depends upon the shape of combining atomic orbitals. Like what is the shape? If spherical are combining, then it will have a different shape. If p orbitals are combining, it will have a different shape. Just as the electron distribution around the nucleus in an atom is given by atomic orbitals, similar way the shape of molecular orbital will also be given by this probability density. Let's talk about that. Okay, let's talk about that. Yes, everybody, what should I answer? Tell me. Ma'am, is it important for class 11 to this particular question? No, if you're talking about you're not preparing for JEE, then definitely not. This is not asked in board exams, but if you're preparing for JEE, so that was a PYQ of JEE, That tells you that it is important for JEE. Right? Now let's see physical significance of MOs. Now, as I told you, there will be constructive and destructive interference, both of them. So if I say that this is psi, this is for 1s, this is the wave function, this is the wave function probability distribution curve. When, because of constructive interference, what will happen? A duplet you will see here, right? That means one peak, then slightly down, then one peak again, and then down. This is your sigma 1s. That is formed by constructive interference. Let's talk about when you have destructive interference. So this is 1s plus, this is 1s minus. So when these two are combined, it will form 1 and 2. This is your sigma star anti-bonding, right? So when plus and plus are combined, that is constructive, that leads to the formation of bonding molecular orbital, right? But when we talk about you have plus and minus, that is destructive interference, that leads to anti-bonding molecular orbital, which because plus and minus are combining, so let's say this is plus and this is minus, so when they combine they will have the formation of a node also here. So this part will be the nodal part, right? Because that will cancel, this particular part will be cancelled here, plus and minus will cancel, right? And hence you will have a nodal plane here. And when you have this, that's the reason what you will have here is, this is psi, and for psi square what you will have, this is defining the node. This is defining the node. This is defining the node. Okay? In anti-bonding molecular orbitals, you have a node there, right? So you have a node here. So when bonding molecular orbitals combine, there is no node here, right? That's why it looks like this, right? But when anti-bonding molecular orbital combine, that means, when anti-bonding molecular orbital is formed, plus and minus combine, they will have a node here that is represented when psi is 0, when psi square is 0. Here, have we drawn this graph already? Psi graph is always positive then negative, right? If you need to draw a node, you will say positive and then negative. For psi square, you will always draw it like this, 1 and then 2, like this you will draw. Similar thing we are doing here. Similar thing. For one node, we will draw it like this. Right? Okay. Hello, Jasveer. Hello, Jas. Hello, Suresh. Now, please focus here. Right? Okay. This now we will do in the next class. Right? This is all I wanted to tell you. That physical significance of these MOs are that bonding molecular orbital is obtained by combining constructive interference, anti-bonding is formed by destructive interference. In anti-bonding you have nodes, in bonding you don't have nodes. Okay? Yes, everybody? Okay. So rest of the part we'll do in the next class, that is about, wait a minute, these things, but before that let's just go through one thing, that is the difference. Okay, let's just go through this difference, and after that electronic configuration, filling of electrons, everything we are going to discuss in the next class. Bonding molecular orbit is the result of linear combination, yes, of AO with their wave functions are added, and here wave functions are subtracted. If it may or may not have nodes. In bonding molecular orbital, if you talk about s orbitals, it will not have. P and D orbitals can have nodes, will have only, right? S orbitals will never have nodes. You can write s orbitals will never have nodes, no nodes in bonding. But in anti-bonding, even S will have nodes, right? Because in spherical, in s orbital, in atomic orbital, it never had nodes, right? In 1s, now also it is in 1s, right? If you talk about nodes, it is n minus L minus 1. In 1s, it is 1 minus 0 minus 1, that is 0. So nodes were 0 in case of 1s. But here in case of 1s also you, in anti-bonding, you in case of 1s also you have nodes, right? So that's why it always have a node between two nuclei bonded atom. This is very important. Atomic orbitals, those atomic orbitals which don't have nodes, in anti-bonding criteria, even the molecular orbitals of those atomic orbitals which never had nodes, in anti-bonding even they will have nodes. Okay, this is a very important point. Then charge density increases between two nuclei, resulting in attraction of two atoms, right? This decreasing between new nuclei, so resulting in repulsion between two atoms. So energy of BMO is less, hence stable. It is ABMO is high, it is unstable. And that's it for today, guys. Right? Okay. This is what I told you, no? That in BMO, in bonding molecular orbitals, you can have nodes or you cannot have nodes. Where you cannot have, in case of 1s, you will not have nodes. We have discussed it. But in anti-bonding, no matter whichever orbital you take, that will have nodes. Right? Okay. So that's it for today, students. Now let me see. Now I'll just give you one homework in the chat. You can just write it down in the comment section. You need to find out shapes of SF6, SF4, SO3, XCF, XCOF4, then PCl3, then what else? I think that's it. You need to tell me the shapes of all of them. In the chat box, in the comment section, the shapes. I'm asking about shapes, not geometry. I'm asking about the shapes of all of them. Right? In the comment section, you need to write it down. Okay? Yes, I'll definitely take that. Okay? Okay, Atharva, yes. Okay, then that's it for today. And students, MVSAT scholarship test. Have you registered or not? Because we are going to take up this scholarship test on 4th, 5th, 11th and 12th of October 2025, and this is Mega Vedantu scholarship program where registration is completely free of cost. But what you need to do here is one thing, that is you need to register yourself, which is totally free of cost. If you don't register yourself, what you will lose, ma'am? You will lose 150 crore worth scholarship. You will lose 2 crore worth prizes and cash, right? That you will lose. 100% free courses, Vedantu free courses. You will have one-on-one counseling sessions. Everything will be totally free of cost if you are among 2.5 lakh students. And if you are a JEE aspirant, then students, the test will consist of 45 questions, 15 questions each PCM. So I would really advise you to register yourself here, right? Okay. Very good. I like your spirit, right? Okay then, guys, now I'll see you all in the next class. Till then, bye-bye, take care, and next class tomorrow at 5 PM I'll take the class, okay? Tomorrow at 5 PM I'll take the class, right? Okay then, bye-bye, take care, see you all, bye-bye.